NASA has announced a discovery of the most Earth-like planet ever found. This out-of-this-world discovery is truly remarkable. NASA says it just found a new planet, which is shocking, right? Indeed, it is. The James Webb Space Telescope, JWST, spotted it just outside of our solar system. For decades, astronomers and dreamers alike have gazed toward Proxima Centauri, the closest star to our Sun, imagining what secrets it might hold. Just over 4 light-years away, nestled within the Alpha Centauri system, Proxima Centauri hosts at least one known planet, Proxima b, long considered one of the most promising exoplanets for potential habitability. Proxima b has remained tantalizingly out of reach until now. The James Webb Space Telescope, humanity's most advanced eye in space, has just delivered the clearest image ever captured of Proxima b. With it comes a monumental leap forward in our understanding of distant worlds. The image arrived like a revelation. At first glance, it resembled what one might expect: a distant orb suspended in the velvet dark. But what made this image unlike any previous depiction of an exoplanet wasn't just its clarity, it was its intimacy. For the first time, scientists were able to observe atmospheric layers, temperature gradients, and possible surface structures on a rocky exoplanet orbiting another star. The sheer precision of JWST's optics, combined with its infrared imaging capabilities, offered an unparalleled window into a planet that has long stood as a beacon of possibility. Proxima b orbits within its star's habitable zone, where conditions might allow for the presence of liquid water. Until now, almost everything we knew about it was inferred: mass, orbit, and proximity. Previous instruments, from the venerable Hubble to powerful Earth-based observatories, gave only shadows and data traces, radial velocity dips, spectral wobbles, and statistical models. No telescope had ever directly imaged Proxima b with any detail, let alone resolution, high enough to distinguish planetary features. That changed with JWST's latest release. What makes the James Webb Space Telescope uniquely suited for such a historic observation is its capacity to operate in the infrared spectrum, allowing it to cut through cosmic dust and glimpse the faintest signals from distant celestial objects. Positioned at the second Lagrange point, L2, it orbits the Sun in perfect tandem with Earth, far from the interfering heat and noise of our own atmosphere. Its mirrors, gold-coated and sprawling, nearly 7 meters in diameter, collect photons with a delicacy and precision that has no equal. When trained on Proxima b, JWST delivered what generations of scientists had only dreamed of: a detailed image not only of the planet itself, but of its relationship to its parent star and surrounding space. The image shows a rocky world slightly larger than Earth, with a landscape that hints at geological activity. There are variations in surface brightness that suggest mountains or large continental ridges. Subtle thermal differences detected across the hemisphere facing its star suggest active weather patterns, perhaps winds, or even something resembling cloud cover. Most notably, JWST sensors detected absorption patterns in the infrared spectrum that suggest the presence of certain atmospheric gases, carbon dioxide, possibly water vapor, and a faint trace of methane, though its identification remains under analysis. This clarity marks a seismic shift in how scientists can study exoplanets. No longer confined to indirect methods of detection, astronomers can now observe and analyze the actual light reflecting from Proxima b's surface and atmosphere. That difference is immense. It transforms the hypothetical into the observable. It moves Proxima b from the realm of theoretical astrobiology into a new phase of empirical exploration. For the first time, a world outside our solar system doesn't just exist in equations, it has a face. What's particularly striking is how JWST's imaging has reshaped assumptions about Proxima b's environment. Early models, constrained by limited data, painted a bleak picture: a tidally locked planet scorched on one side and frozen on the other, with a thin or non-existent atmosphere stripped away by stellar flares from its volatile red dwarf star. But the JWST image complicates that narrative. Thermal imaging across the planet's surface shows a surprising uniformity of heat, implying the presence of an atmosphere capable of redistributing warmth. That, in turn, opens the door to discussions of climate regulation, cloud formation, and, most tantalizingly, the potential for habitability. The implications extend beyond Proxima b itself. This single image sets a precedent for what the James Webb Space Telescope can achieve in exoplanetary science. Proxima b has long been the poster child for potentially habitable worlds due to its proximity and Earth-like characteristics, but there are countless other planets awaiting the same treatment. Some even closer in size and composition to Earth, others located in even more stable stellar environments. JWST's success here suggests a future in which imaging a broad catalog of exoplanets becomes routine. There's a quiet poetry to this moment. Humanity, perched on its pale blue dot, has turned its gaze outward and, with new clarity, glimpsed a sister world. The image of Proxima b doesn't just represent a planet, it embodies the enduring curiosity that propels exploration. It's a snapshot of possibility, of what might be. For those who've dedicated their lives to studying the cosmos, the arrival of this image is a moment of validation and awe. For those just discovering the wonders of the universe, it's an invitation. The technical achievement is staggering. The stability required to maintain a lock on a point of light 4 light-years away. The precision needed to isolate planetary features against the brightness of a nearby star. And the data processing techniques to decode faint infrared signals. All of these are marvels of engineering and software working in concert. The success of this mission is not just a testament to human ingenuity, but to decades of international cooperation, planning, and persistence. JWST's image also hints at something more philosophical. If we can see Proxima b this clearly, if we can detect signs of weather, gas, and geology, we're beginning to cross a threshold where exoplanets are no longer speculative destinations, but tangible places. They're not just out there anymore. They are somewhere, with surfaces that may host winds, rain, valleys, and perhaps even the rudimentary ingredients of life. The emotional weight of that realization is difficult to overstate. It changes how we think of space, not as a void, but as a vibrant tapestry of diverse, dynamic worlds. In scientific circles, the reaction has been electrifying. Researchers are already combing through the flood of data accompanying the image, seeking to refine models of planetary evolution, atmospheric chemistry, and orbital dynamics. The spectral data hint at complex interactions within Proxima b's atmosphere, possibly even photochemical reactions driven by its red dwarf star's intermittent flares. Some teams are exploring how these interactions might affect the long-term stability of any biosignatures. Others are considering how this image might inform future missions, including those proposing robotic probes or even interstellar sails. One of the more provocative discussions sparked by this image centers on habitability. If Proxima b possesses a stable atmosphere and surface temperatures capable of supporting liquid water, then it is, by definition, within the threshold of habitability as we currently understand it. But habitability doesn't just mean Earth-like conditions. It means the potential for ecosystems, for chemistry to evolve into complexity. The clearer the picture becomes, the more the conversation shifts from "could life exist" to "how might it look, function, adapt?" There's also growing interest in how JWST's imaging might aid in comparative planetary science. Proxima b, while unique, shares traits with many planets both in our solar system and beyond. By comparing its features to those of Mars, Earth, or even Venus, scientists can refine their understandings of planetary development. Did Proxima b experience a runaway greenhouse effect? Is it in a geological phase akin to Earth's early Archean eon? Has it retained tectonic activity? These are no longer abstract questions. With high-resolution imaging and rich spectral data, they become testable hypotheses. The clarity of the image has also ignited renewed discussions about future exploration missions. Proposals like Breakthrough Starshot, which aims to send tiny light-propelled probes to nearby stars, now seem less like distant dreams and more like logical next steps. If a planet just over 4 light-years away can be seen in this much detail, then launching microscale explorers to gather in situ data becomes a goal within technological reach, if not now, then within decades. Educational institutions and planetariums are already adapting the new image into their exhibits and curricula. For the next generation of scientists, Proxima b won't be a mysterious dot in a textbook. It will be a world with color, contrast, and character. This shift from abstraction to visualization is powerful. It transforms the way we teach, learn, and inspire. It becomes easier to explain the importance of planetary science when you can point to a real place and say, "We've seen this world." While many details still await confirmation and deeper study, one thing is clear. This image is a beginning. It's the dawn of a new chapter in exoplanetary science, one where observation and imagination walk hand in hand. The technology behind JWST will continue to evolve, and future instruments on Earth and in orbit will build upon this foundation. But nothing can replace the first moment when the universe opens its curtain and reveals something hidden, something long suspected but never before confirmed. Every pixel of that image tells a story of starlight traveling 4 years through space to reach a floating mirror of gold, a story of how that light was split, measured, and mapped with extraordinary care, a story of data turned into vision, and vision turned into understanding. It is a triumph of science, of technology, and of the collective spirit of exploration that refuses to settle for ignorance. In the coming months, the image of Proxima b will be analyzed from every angle. Spectroscopic data will be parsed, thermal maps refined, and every visible anomaly scrutinized. There will be debates, revisions, breakthroughs, and probably a few surprises. But the most profound impact may be on the human imagination. Seeing a distant, possibly habitable planet in such clarity expands the realm of the possible. It invites not just scientific inquiry, but cultural reflection. It forces humanity to re-examine its place in the cosmos, not from a position of isolation, but of connection. For now, the image of Proxima b stands as a symbol of what we can achieve when curiosity meets capability. It's a reminder that the universe is not just a cold expanse of stars and silence, but a dynamic theater filled with unknown actors waiting to be discovered. With the James Webb Space Telescope as our instrument, we've taken one more step into that darkness and found not emptiness, but wonder. The unveiling of Proxima b in such exquisite detail is more than a technological milestone. It represents a deep psychological and cultural turning point. Until now, exoplanets were largely the realm of the invisible, scientific extrapolations drawn from dips in starlight or wobbles in a star's motion. This new image shatters that abstraction. For the first time, humanity has visually encountered a terrestrial world outside our solar system. It has gone from idea to artifact, an object with color, temperature, and texture. This transformation changes how we relate to the cosmos and to the very idea of planetary neighbors. There's an almost mythic weight to this moment. For centuries, the idea of other Earths haunted human thought, whispered about in the pages of early astronomical treatises, speculative fiction, and philosophical musings. Proxima b, as seen through the lens of JWST, gives those centuries of speculation a concrete anchor. Here is a world orbiting a nearby star, visible not as a data stream, but as a planetary disk resolved by a machine built to fulfill humanity's oldest longing: to look beyond the horizon. As astronomers continue to examine the details of the image, attention has naturally turned to questions of planetary dynamics. Proxima b's orbit is incredibly close to its host star, completing a full revolution in just over 11 Earth days. From such proximity, it would receive a constant bath of stellar radiation, particularly in the ultraviolet range. With JWST's data, researchers now have the tools to evaluate how that radiation interacts with Proxima b's upper atmosphere. This helps determine whether the planet has retained enough of its protective envelope to shield any potential biospheres below. The early readings suggest some degree of atmospheric retention, an unexpected outcome given the traditionally violent behavior of red dwarf stars. The scale of radiation interaction also opens up new frontiers in exoplanet climatology. With the imaging and spectral data obtained, scientists are crafting the most detailed climate simulations ever run for a world beyond our system. These models are incorporating JWST's thermal and photonic inputs to simulate everything from daylight circulation patterns to long-term climate feedback loops. This could tell us whether the planet suffers from extreme temperature swings, whether its weather operates in cyclical patterns, or whether it could maintain climate equilibrium conditions necessary for habitability. One of the more surprising findings buried in the early image data is the suggestion of surface heterogeneity. Differences in reflectivity, known as albedo, across various portions of Proxima b hint at the presence of varied terrain. Some areas reflect more infrared light, possibly due to icy or mineral-rich surfaces, while others absorb it more completely, suggesting darker basaltic regions. This patchwork texture could imply a complex geological history, perhaps shaped by tectonic or volcanic forces. If these interpretations hold, Proxima b is not a dead rock, but a geologically active world. Geological activity is more than a curiosity. It is one of the cornerstones of planetary vitality. On Earth, plate tectonics help cycle carbon between the mantle and the atmosphere, regulating temperature and atmospheric composition. Volcanism releases vital gases that can contribute to atmospheric replenishment and even seed primitive chemistry. The suggestion that such processes might also occur on Proxima b opens up a whole new set of questions about planetary evolution across the galaxy. And there is the tantalizing idea that if geology is active, then so too might be hydrology. Although JWST cannot directly detect rivers or lakes, the inferred presence of a stable atmosphere and the planet's location in the habitable zone raise the possibility of surface water. If water exists, and if it has persisted for geologically significant timescales, then the door cracks open to the potential for life. Life, of course, remains the ultimate question. While JWST is not specifically designed to detect life, its instruments can pick up chemical markers, gases like methane, ozone, or combinations that are hard to explain through abiotic processes alone. While no such definitive biosignatures have yet been confirmed in the data from Proxima b, the presence of carbon-bearing gases and the possible detection of water vapor make the planet a prime candidate for continued observation. With the clear image now in hand, the possibility of targeting Proxima b for future missions has grown stronger. Astrophysicists and aerospace engineers are re-evaluating the feasibility of sending lightweight probes propelled by light sails, a concept once dismissed as theoretical indulgence. Now, with a visible destination, these concepts gain traction. A probe traveling at 20% the speed of light, a speed theoretically achievable by laser-propelled sails, could reach Proxima Centauri in just over 2 decades. What once felt like the stuff of science fiction is inching closer to scientific plausibility. The image has also ignited a cultural shift. Artists, educators, and filmmakers have already begun reimagining their portrayals of alien worlds in light of JWST's revelations. No longer bound by fantasy or extrapolation, they now have a real-world template, one with peaks and shadows, with atmospheric haze and varied terrain. The human imagination, always hungry for tangible inspiration, now has its first true exoplanet portrait. The shift from imaginative rendering to visual reality is profound. It bridges the divide between scientific data and human perception. Public reaction has been similarly intense. Online communities have flooded social platforms with discussions, fan interpretations, and layperson analyses of the image. The moment the image dropped, it trended globally, drawing in not only astronomers, but everyday people curious about the wider universe. For many, it was the first time they had seen an actual visual of another potentially habitable planet. The psychological impact of such a moment, quiet, awe-filled, and communal, has already been compared to the Apollo 8 Earth photo or the famous pale blue dot captured by Voyager. That sense of scale and perspective is what makes JWST's image of Proxima b so important. It's not just a scientific achievement, it's a cosmic mirror. For those paying attention, it is an invitation to humility. Here is a world orbiting a faint red sun, likely unknown to anyone or anything that might inhabit it, now seen for the first time by a distant species that only recently mastered spaceflight. It places our struggles, our triumphs, and our questions into stark relief. We are not the center. We are not alone in our planetary experience. Back in the lab, researchers are focused on refining spectral analysis. Every tiny variation in the light coming from Proxima b is being dissected for information. They're studying isotopic ratios that might indicate the origin and longevity of the atmosphere. They're modeling how light reflects off different surface minerals to better estimate the planet's composition. The goal is to build not just a picture, but a planetary biography, to chart how this world came to be, how it evolved, and what its current state can teach us about planetary formation more broadly. Meanwhile, other teams are using the Proxima b image as a template for designing new instruments and missions. Adaptive optics on ground-based telescopes are being fine-tuned to match JWST's output. Proposals for next-generation space telescopes, such as LUVOIR or HABEX, are incorporating lessons learned from the Proxima b imaging process. Future observatories will aim not just to match, but to surpass what JWST has done, targeting even smaller exoplanets and attempting to resolve finer details like cloud structures or even surface liquid signatures. The implications for planetary classification are also significant. Proxima b has long defied easy categorization. It's a rocky planet in the habitable zone, but its size places it slightly above Earth's mass, straddling the line between Earth-like and super-Earth. The image provided by JWST offers crucial insight into whether these larger-than-Earth terrestrial planets form and evolve like our own, or follow different developmental paths. The answer could reshape how we search for life and which planets we prioritize in future surveys. New fields of inquiry are opening as well. Comparative exogeology, analyzing geological processes across planets outside our solar system, has been a field limited by data scarcity. Now, with detailed imaging of terrain from another star system, geologists can begin comparing erosion patterns, fault lines, and impact craters across interstellar distances. The idea of building geophysical models that span not just planets, but star systems is breathtaking. It speaks to the expanding scale at which science can now operate. From a sociological perspective, the image has spurred debates about space policy and ethics. If Proxima b shows signs of habitability or even simple life, how should humanity proceed? What moral obligations do we have to distant ecosystems? Would sending probes or eventually landing humans constitute interference? These questions, once purely speculative, now feel immediate. As our observational capabilities improve, so too must our frameworks for engagement with alien worlds. Educational systems are also beginning to shift in response. Astronomy departments at universities are rapidly updating their coursework to include modules based on Proxima b's image data. High school science teachers are using the image to spark student interest in STEM fields. Planetariums are designing immersive exhibits that allow visitors to stand on Proxima b's surface as imagined through JWST's lens. The image is not just a scientific artifact, it's a teaching tool, an inspiration engine, a doorway into curiosity. And the influence does not stop there. Policymakers and funding bodies are now faced with a vivid, concrete result from decades of investment in space science. The success of the JWST, as exemplified by its Proxima b image, will likely serve as a rallying point for increased funding into astrophysics, planetary science, and space exploration initiatives. It validates the cost, the complexity, and the time these projects require. It proves, in high definition, that the results are worth it. In literary and philosophical circles, the image has begun to influence discourse around the Anthropocene and humanity's relationship to Earth. If there are other rocky, Earth-like worlds nearby, then what makes our own planet special? Are we caretakers of a unique biosphere, or merely one thread in a much larger cosmic tapestry? This shift in perception could influence everything from environmental ethics to international cooperation, from theology to speculative fiction. As data continues to stream in, and as computational models grow more refined, what comes next may be even more astonishing. we may not only learn about Proxima B's climate and chemistry, we may begin to chart its seasons, detect weather events, or spot geographical landmarks. With further study, even a faint glint from a surface ocean could one day be within reach. The clarity we now have will only improve as techniques advance, and with it, our understanding of this other world will deepen. We are now witnessing the birth of interstellar geography, not just maps of stars and voids, but of real, tangible places with contours, conditions, and potentially communities. Proxima b has become more than a destination. It's a presence in our collective consciousness, a shadow now turned to silhouette, and soon, perhaps, to full form. The James Webb Space Telescope has opened the gate. What lies beyond it is the work of generations. But it begins with a single stunning image of a world we can finally see. And so, Proxima b becomes our first real bridge to the stars, a planet that, despite being impossibly distant by human standards, now feels close. Not because we've traveled there, but because we've seen it. We've captured its light, decoded its heat, and glimpsed its contours. For the first time in history, another rocky world has stepped out of theoretical shadow into observable reality. In that single act of imaging, a new era of exploration has begun, not with rocket fuel or landers, but with mirrors, photons, and the unyielding curiosity of the human spirit. As scientists continue to examine every nuance of the James Webb Space Telescope's landmark image of Proxima b, a new domain of investigation has emerged: planetary time. The high-resolution data has offered not only a spatial snapshot, but also temporal clues that hint at how Proxima b might have evolved over billions of years. The patterns in the light it reflects, the thermal gradients across its surface, and the composition of its atmosphere may each carry the imprint of a long and turbulent history etched in planetary time frames. Researchers are now modeling what Proxima b may have looked like in the past and what it could become in the far future. In doing so, they're reconstructing the biography of a world stage by stage, eon by eon. This leads to a profound scientific benefit: comparative planetary timelines. Earth's geologic eons, from the Hadean to the Anthropocene, are well studied, but extrapolating those timeframes to an exoplanet demands a reference point. With this image, scientists can begin to track the evolutionary arc of rocky exoplanets under the influence of red dwarf stars. Are they slower to cool internally? Do they retain heat differently due to their mass or orbit? If Proxima b exhibits features of a young volcanic planet, or conversely, a geologically dead world, it provides a key puzzle piece for establishing time-dependent models of planet evolution across various stellar environments. Now that we can see Proxima b with such fidelity, astronomers are exploring the possibility of subtle seasonal variations. Though the planet's orbit is tight and its tilt likely minimal, even small changes in its orbit or axial alignment could generate long-term climate shifts. JWST's data will be monitored over months and years to detect any signs of these cycles. Tracking such seasonal rhythms, if they exist, would be yet another layer of complexity previously unimaginable in exoplanet science. It would transform Proxima b from a static sphere to a dynamic system undergoing slow but measurable climatic evolution. Another groundbreaking area of exploration now made possible involves cloud physics. The clarity of the atmospheric imaging suggests stratification, different layers of gases interacting with light at different intensities. This implies not only an atmosphere, but an atmosphere with complexity, one potentially capable of forming clouds. Unlike Earth, where water clouds dominate, Proxima b might feature clouds of carbon dioxide, methane, or exotic chemicals unknown in our skies. The optical scattering and thermal absorption patterns observed point to suspended particulates or aerosols, possibly generated by volcanic outgassing or photochemical reactions. These clouds, if confirmed, offer more than a visual clue. They represent an entire atmospheric system, a mechanism